Right, 67 people are there, so I think we will get started because otherwise it's not a great idea to keep them waiting.
Okay, sir, then let's start.
The floor is yours, Rohan.
9:30, yes, so 9 o'clock there, right?
Okay, sir. Hello, everyone. I'm Rohan, one of the coordinators of the Society of Civil Engineering. You all are most welcome in the today's alumni session, in which we call various IITK alums from the different fields so that students could gain knowledge from them. And today we have Mr. Raj Bhattarai sir amongst us, who is going to give presentation on the future on water forwards, which is Austin Water's 100-year future plan. Mr. Rajendra Bhattarai sir is the president of Clean Water Strategies in Austin, Texas, USA. He has more than 45 years of experience in water quality management and water resource recovery, almost 35 years of which were at Austin Water. He received his B.Tech in Civil Engineering from the IIT Kanpur and M.S. in Environmental Health Engineering from the University of Texas at Austin. Mr. Bhattarai sir was a visiting professor of Civil Engineering at IIT Kanpur from 2019 to 2021. He served as the president of the Water Environment Association of Texas and the Texas Association of Clean Water Agencies as a board member of the Water Environment Federation, the National Association of Clean Water Agencies, and also of the Water Environment Research Foundation, where he even chaired the Research Council. He is currently a board member of Water Systems Consulting, headquartered in California. Mr. Bhattarai is the recipient of Glasgow Medal and the Bedell Award from the Water Environment Federation. He also received the Lifetime Achievement Award, the Pillars of the Profession Award, and Mealy Award from the Water Environment Association of Texas for the significant contributions to the art and science of wastewater management and water pollution control. A distinguished alumnus of the Civil, Architectural, and Environmental Engineering Department of the University of Texas at Austin. I would also like to bring everyone's notice that Mr. Bhattarai has almost 160 presentations and publications to his credit. Now I would like to request Raj sir to continue from here.
Well, thank you very much, Rohan. Thank you for the introduction, and I thank the Society of Civil Engineers for inviting me to give a talk here. It is a pleasure to be, with the people, the students there at my alma mater. And I also want to begin by thanking Dr. Sudhir Mishra, Professor Sudhir Mishra, for introducing me to SoCE, with Rohan and others. And so with that, I am going to talk about what we did at Austin Water. The work was completed just before I retired. I retired from Austin Water at the end of September. September 30, 2018 was my last day. And we had pretty much wrapped up the work for this 100-year plan. Generally, when we make plans, plans are usually for 10, 15, 20 years into the future. Some go to 40 or even 50. But the most common plans are about 20 years into the future, because too far into the future, technology changes, things change, so there are too many uncertainties. But because of climate change and the extreme weather events we're seeing, extreme drought and extreme flood, and extremely high temperature and extremely cold temperature, both ends of the spectrum. And that every one of those events affects the water supply. So we figured we had to do something to plan for and Austin is growing very rapidly, as you will see. We figured we really need to plan, and then the short-term plan will not do, especially with the climate change that is happening. What is going to happen? We had to decide, and then we decided to be very bold and took an unusual step of doing a 100-year plan. We're not saying that stay as it's a fixed plan, because in 100 years, as I said, a lot of things will change as the technology changes. So there are mid-course checkpoints and corrections that we can make. So the plan has to evolve in the future. The plan has been designed like that. So anyway, so with that little bit of introduction, let me begin. So it's been particularly gratifying to me to speak to SoCE, because I used to be a member of SoCE when I was a student there. And here I actually found my membership card from 1974-75. I've kept a lot of my books and my notes from my IIT Kanpur days, even all these years later, 50 years later. I was not able to, however, find my 1975-76, my final year card. So this will have to do. And kudos to the people at SoCE at that time. The membership card, the aspect ratio exactly matches the widescreen format for a PowerPoint, as if they knew I was going to use this. And this is, when I scanned it, it fit exactly into the screen. I didn't have to crop anything, here to make it fit. Anyway, so with that little bit of introduction, let's begin. So, and I want to begin by acknowledging my former colleagues at Austin Water. Marisa Flores Gonzalez, she was the project manager. Dreama Gross was in charge of conservation. Teresa Lutz was the manager of the water planning group. And Robert Stefani was also in the water conservation group. These people played a major role in developing the plan. I had a very small role. So, but hey, I'm love presenting on this because this is a really good achievement. You can see the Google building here. So Austin is become a high-tech mecca. A lot of the big high-tech companies are here. Tesla just moved here recently, started manufacturing its electric cars. Every company, Apple, Amazon, Facebook, you name it, they're all here. So where is Austin? You can see it's the capital of Texas. It's one of the southernmost states. South, there is Mexico. Could you all please mute your microphones? It is the 10th largest city in the US, but US is not as big as India, so 10th largest city in India would be a humongous city, whereas here Austin had about 1 million people and becomes 10th largest. Million is only 10 lakhs, right? But the metro area population all around, if you put the suburbs in right next to Austin, it's about 2.4 million. And it is growing very fast. It's one of the most desirable cities to live in the US. And about 180 new people move in daily. So that poses quite a challenge to the water department to expand the water network to provide water to all these new people who are moving in, both water and wastewater. And it's also the capital of Texas. And so there are a lot of the state government offices and employees are here. And the Texas State Senate and the Texas House of Representatives, they're all housed here. And of course, it's the home of the University of Texas at Austin, very large university, more than 50,000 students in one campus. That's the largest campus of the University of Texas system. So here's a photo of the campus. And in fact, I came to Austin to go to attend the graduate school at the University of Texas at Austin and got lazy and never left and stayed here. So the population of Austin has grown from the first census was in 1840. You can't see it here. The first census, Austin was founded in the 1830s. Earlier it was just a stop on the way for people going in on the bank of the river. And when the European settlers started settling here, they found this river, and then right next to the river, they decided to make a settlement. The Austin was registered as a city in 1839, and then the first census came in 1840. At that time, there were like 553 people. In 1977, when I came here, the population was about 320,000. And now we're close to 1 million now by 2022. So it's been a pretty rapid increase in population, as you can see here. So that creates a challenge. A little bit about Austin Water. Our service, we provide water and wastewater service to about 1 million people. That is about 10 lakh. Our operational maintenance budget is about $650 million per year. And the 5-year CIP stands for Capital Improvements Program. This is to build new projects and upgrade older facilities. We spend almost $1 billion every 5 years, so about 200 million every year on building new facilities to pay for growth, expand the treatment capability, make improvements. And the average water and wastewater bill is about, almost $80 a month for an average customer pays that much. Out of which, but maybe 60% or maybe 65% is wastewater, and about 35% is water. Wastewater is much more complicated to treat and requires more energy. And so that's why wastewater is more expensive. We treat the wastewater so well. It provides exceptional water quality around Austin. Our drinking water source are Lake Travis and Lake Austin, that's on the Colorado River. This is not the Colorado that makes the Grand Canyon, not the Colorado that originates in the state of Colorado and then flows through Nevada and then California, Arizona, and then ends up in the Pacific Ocean. This is the smaller version, the Texas version of the Colorado. It originates in Texas and ends up in the Gulf of Mexico. Sort of flows from northwest to the southeast. So we provide drinking water, wastewater, and reclaimed water. The treated wastewater is also used for industrial, for irrigation, agricultural use, or for commercial use, where you don't have to use drinking water. So that's our reclaimed water program. So we have, in a way, it's one utility has three utilities: drinking water utility, wastewater utility, and a reclaimed water utility. And our service area is about 1,400. I forgot to update. This is about 1,450 now. Probably the city is growing, but 1,450 square kilometers. And we serve about 1 million people. And the utility has about 1,200 employees. I want to begin. I already mentioned earlier because of extreme weather, but extreme weather is pretty normal, has been normal for Texas, but except it's getting more pronounced now. In 1927, I don't know, some unnamed anonymous state meteorologist had said this: Texas is the land of perennial drought, broken by the occasional devastating flood. It's a pretty good description, especially for this San Antonio, Austin corridor. This area, we get what they call flash flood, meaning almost like in a flash, you get so much rain. Austin gets average of about 32 inches of rain a year. But sometimes in one night, I've seen 13 inches of rain fall in just one single night. In about 8 hours, 13 inches. So that's a huge amount of rain, so falling so quickly. This part, for some reason, well, the geographical, the topography is like that. There's a sudden, there's a fault, and then the ground sort of rises very sharply. Because of that, when the clouds from the Gulf of Mexico come with the moisture laden cloud, they hit that, they're pushed up, and then you get a lot of rain here. So this area is notorious for flash flooding. People say don't drive when there is a lot of heavy rain, because you really have to be careful. Suddenly your car could get washed away. But this used to be the norm, but now it's become even more extreme because of climate change. So we're seeing more extreme flood, more extreme drought. So here is the sort of really the lakes I was talking about. There are more series of lakes upstream also. So they're called Highland Lakes. They're formed by the Colorado River. This used to be the river. And these dams were built in the 30s and 40s, right after the Great Depression, when Franklin Roosevelt became a president here. He started a massive construction program to keep people employed. So these dams were built at that time to control flood, because Austin used to get really badly flooded before these. So they were built in 30s, and finally in 40 or 41, these were all complete. So that has some implication that I'll talk about later. So this is the largest lake. And then after that, there's more of a riverine lake. This is also a lake. There's a small dam here. And there's another riverine lake. This is right downtown in the middle of the river. The picture you saw in my earlier photos, that was the Ladybird Lake, or it's called Town Lake. So our three water plants are the Davis Water Plant from 1954, the Ulrich Water Plant from 1967, and then the Hancock's Water Treatment Plant, our newest plant on Lake Travis, that was completed in 2014. So basically the river comes this way from the northwest, flows to the southeast. So you'll see that the plants are here. This is the river, the Lake Travis, Lake Austin, and so these are the plant, and this Austin is all around here. These are the suburbs. So these are the capacity, and the total capacity is about 1,268 megaliters per day. But our historical peak day pumpage was in 2005. After that, our water usage has gone down because we have pushed conservation quite a bit. We're asking people to conserve, and the people have listened. And then the drinking water distribution system, pretty large network of pipes. We have reservoirs and pump station in different neighborhoods because you don't want to pump from one central location. Suddenly, if there is a fire in some area and you need a lot of water, so you want a tank nearby to supply the water. Otherwise, the water pressure may not be adequate for everybody else. So that's why we're strategically placed 41 different reservoirs throughout the city, 28,000 fire hydrants, and there are almost 225,000 water service connections. The wastewater system is big. Again, the collection system is 4,700 kilometers. And then the private lateral, the pipe coming from the house up to the street connecting, those are privately owned and privately maintained. That's also about the same length. A lot of manholes, because Austin is a hilly area, you have almost 140 lift stations to pump the wastewater sewage over the hill, and 3 large tunnel interceptors. These are 96-inch in diameter, but 2.44 meter. Big odor control units to make sure the thing doesn't stink up the whole neighborhood. About 200,000 services, and you see that that's less than the services for drinking water, because some people are on septic tank. They get the drinking water, but they don't return their wastewater to our system. And then there are 2 large wastewater treatment plants. They are 75 million gallons a day each, 284 million megaliters per day. There are 9 smaller treatment plants. In the system, these are really small plants. System-wide treatment capacity is 587. And then our wastewater flow is less than that, of course. So we have adequate capacity. We keep expanding the plant to keep up with the growth. And the wastewater system is a separate system. A lot of the older cities have the stormwater, like the storm drain, as well as the wastewater sewage flows through the same pipe. We call the combined sewer. Whereas we have a separate sewer system, separate collection system. So the stormwater thing is separate. The sanitary sewer is separate. It's a separate pipe. And then, look at the manholes made in India. A lot of manholes here are made in India. So I have a whole collection of manhole covers from all around the world. That's sort of become my hobby. Whenever I go visit a new place, I see something different, I always take a picture. And so this is from one of my collections. This is actually from Austin, of course. So most of the primarily by gravity, but then there are, I told you, 139 lift stations. When you come to a hill, you have to pump. So that's the wastewater system. And let me go back, sorry. So because the stormwater, the rainwater drainage that goes straight to the river without treatment, that's why they put the signs there saying no dumping drains to creek, because that's sort of a warning to people saying, hey, if you put anything here, put trash or use motor oil or any chemicals, that'll end up in the river and will go into our drinking water. So this is a public education thing. We do that. Whereas the one from sanitary sewer, the manhole, that what flows under there, that goes to the wastewater treatment plant. So these are the treatment plants, 2 large plants and 9 smaller plants, the total treatment capacity and the total wastewater flow. I think we talked about that. So here are the plants. You notice the water treatment plants were located on the left side of the frame, meaning on the west and the north side. And because the river flows this way, so obviously you want your water treatment plant at a higher location and let it flow by gravity. And then the wastewater is collected by gravity, and then in this area where the river is flowing towards. So, and then most of the wastewater plants, the major wastewater plants are here. But there are these smaller plants which serve different neighborhoods. They were built by private developers when they developed the neighborhood. And some of them basically use their wastewater to irrigate the golf course. So they don't discharge, but some of them do. So, but they're scattered all throughout. But these are really tiny little plants. And then all the sludge, the biosolids, what we call biosolids, are collected from the wastewater treatment and goes to one central location called Hornsby Bend. There we digest it in anaerobic digesters, create biogas, methane, and we generate electricity with it. There is enough electricity to supply the power need for the entire plant. And then we have some extra electricity, we put that back into the grid. We also do, there is a Center for Environmental Research with the University of Texas at Austin and Texas A&M University, two of the largest universities here in Texas. So that is that. And the return after wastewater and the urban area is exceptional and better than upstream. Generally, when you have a large city, the water quality degrades because of the trash and the wastewater that goes in. And so let me just show you an example here. The Lake Travis has exceptional quality water because it's a large lake. A lot of the solids settle down. The water clarity is good. Water quality is also better. Lake Austin and Lady Bird Lake are only high quality. They don't have the exceptional quality water because now the city's effect is start to feel on this one. But then downstream of here, where we discharge our treated wastewater effluent, this one is again exceptional. This is better than high. And so some of my friends and colleagues, some say, oh, so you put your discharge, your dirty, poopy water into the exceptional quality, water quality segment. And I tell them, no. Our exceptionally treated effluent is helping make this exceptional. Otherwise, these two segments would also be exceptional. So we have basically, this is what is making this exceptional. So this is a very proud thing. And I always joke that Austin is #1 and #2 because of that. And then the water reclamation, I told you about the third utility. We use purple pipe because the treated wastewater looks so clean and good. It's really difficult to distinguish from drinking water. So to avoid that, we use this purple water. And we're using not a whole lot, about 3 to 5% right now, but there's a lot of demand is growing. Like Tesla is going to use a lot of our water. There's a lot of other plants. In fact, Tesla has built its plant right next to our South Austin regional plant. Started operating just last month. So this is a tower for water tower for tank for supplying for this reclaimed water tank. Water conservation, we knew in Austin, in Texas, it's not a very wet place, dry, a small river. So we started pushing water conservation beginning in the 80s, and it really took a forefront in early 2000. And we encourage people and a lot of money in education. And so you can see our water use used to be more than 200 gallons a day. This is sorry, it's in gallons, not in liters. Unfortunately, US is the only country which is still using the British system. Even the British don't use it.
Very good.
So that's the sad thing. So I've converted wherever possible in liters, but this one is just didn't make much sense. Anyway, so it used to be 200 gallons a day. Can you imagine? That's a lot of water. And so now it has come down to about 120. It's settled here in the last few years. This is where we are now. So that's still a big drop, which we can do a lot better. Most countries don't even use 200 liters per person per day, and we're using 200 gallons per capita per day. I mean, or 120. That's also a lot. So we should be able to go down. I don't use that much, but that's a different story. And so basically, what prompted us to go into the 100-year plan was the really extreme weather condition in 2011, which was the hottest year on record for Austin. We had but 90 days, not about, like exactly 90 days above 100 degrees Fahrenheit. Usually on an average, Austin gets about 12 to 15 days of 100+ degree temperature. This is Fahrenheit, of course, not Celsius. We're not boiling, even though it feels like that sometimes during the summer. And it was also the driest 12-month periods in Texas began keeping records in 1895. And then there was record low inflow amounts into the Highland Lakes, the lakes which are the source of our drinking water, and record high electricity use. So generally, we only get 12 to 15 days of 100+ degree triple-digit temperature here, but we have 90. Imagine 90 days is like 3 months, which is whole 1/4 of the year was more than 100 degrees. It was amazing. It was unbelievable. So it's very, very high temperature, and of course that meant drought, and not just that, it created a lot of fire in 2011. So right in the suburbs in Austin, I know one of my employees completely lost his house and farm. They used to be in this Bastrop area, and another employee, she had to run literally because the fire was coming to her ranch. She had about 25-acre ranch where she had horses and cows. She basically had to cut them loose. She opened the ranch door and let them run away, but they came back, unfortunately. And she cried and called me. I said, okay, I'm going to come pick you up. But she lives 40 miles away from here. So as I was driving, and then she called me back saying, well, one of her neighbors came and picked her up, and then they're going to another friend's house for safety. And she survived. Her house luckily survived. But unfortunately, one of my employees completely lost his house. And he used to have this old tractor collection. He had like 15 really old tractors in amazing mint conditions. They were all gone. His insurance, I think, paid a little bit of money, but it was very tragic. So there were a lot of homes were damaged. This was the largest wildfire in Texas history. So all of this, and then the Lake Travis, which was the largest lake I showed you, this is what it looked like in July. The lake used to be full. Look at the dam level is up here, but you started seeing islands in the middle of the lake where nothing would be there. But these were all used to be submerged, and so this is what happened. The lake was down to about 30% of the capacity. And this is the same place, by the way. I wish I had foreseen this, and I would have taken a picture before when it was full, but so I had to go back and take these pictures later on. So 2011, I took this picture. Now look at this 2016. Same point, how full the lake is after the big flood. Again, another thing on another point on the this was all this, the water level used to be up to here. That's all completely exposed. Only 30% of the lake is full. The same point in 2016 after a flood, after when the lake was full. This is where it happens. This is what I'm talking about. And here's another location. This one, exactly the same location. Look how full this is. This is the normal operation. This is abnormal. This is the drought. And this is the Pyronellis River. Remember the name of this river? This is a small river that comes into the Lake Travis, the large thing, because this creates havoc for us in 2018. This was a trickle. You could jump over it. And the same Pyronellis River, exactly the same location. It's the same location. You can see how full it is in 2016. Anyway, so the main point of those photos are basically to show the recent extreme events and the drought and flood. So the lake levels fell to nearly 30% capacity. So we tried water conservation, and when people saw that, people of course started using less water. So, but when people use less water, that means our revenue goes down. So we lost $60 million. So all of a sudden we had to change our budget because our budget was already approved. So we had to make changes in our budget because money wasn't coming in. But we still kept pushing people not to use water because we had to save the water. We couldn't have, at that time, the 11th largest city, now it's the 10th largest city. We couldn't tell people saying, okay, sorry, no water, so everybody leave. We can't, so we couldn't do that. So we had to do something. So we started looking at other sources of water, basically source of water through water conservation, through reclaimed water, the treated sewage, basically, or aquifer storage and recovery. You treat the the drinking water from the river, and you store it during heavy flood condition. You store it and you inject it into an aquifer, and then that way it doesn't evaporate, like unlike in a dam, because in dam you can, in a hot place like Texas, 18-20% of the water can evaporate, whereas in the aquifer you can get 95 to 98% recovery. So if you find the right type of aquifer, and of course using groundwater, we've never used groundwater here in Austin. We only use surface water, and then stream augmentation using reclaimed water for augmenting the water supply. So we looked at all of these. The IPR is indirect potable reuse. You treat the wastewater, create the reclaimed water, and then instead of connecting it directly to the drinking water plant, you put it in a lake or a river, and then you withdraw it downstream, and then that's the indirect potable reuse. So we decided to do a 100-year water plan because of this problem I told you earlier, to reflect the community's values, to ensure a diversified, sustainable, and resilient water future with a strong emphasis on water conservation. And then planning for drought and climate change. And then the city council appointed task force. They met every month. And then there was a tremendous coordination between different departments and the different communities. We went throughout the community. We held hundreds of meetings with neighborhoods and community people, residents there, to get their input, and then explaining our ideas, and then made changes. And the plan was projected to be completed in mid-2018, by the summer in 2018, and so delayed by a few months. It was completed in September, and then with planned updates for a 5-year cycle. So we have our rights, water rights. Because of seniority, because we've been here for a long time, so we can pull up to 325,000 acres. Sorry, there's no metric units for this. These are acre feet per year. Basically, 1 acre of land with 1 foot of water there, that would be 1 acre feet. And so that's 325,000 acre feet. We have that much right. But basically, the LCRA, the Lower Colorado River Authority, they control the river, and we have to pay them. We paid them fees and bought. And if you start using more water, there's an extra charge they do. So that's why we had to, because if everybody starts pulling the water and the river goes dry, then nobody has anything. So they have to basically adjust the prices. As you use more water, you pay more and more price. So we have to do that, and we have to do that to our customers, to all the residents also. So the recent extreme drought, Austin's growth and development, climate change impact, and sustainability principle, all of these were impact further. So we called it the Integrated Water Resources Plan. I told you the changing climate in Austin, higher temperature, higher evaporation, and increased drought intensity. And this is downtown Austin. It flooded. Look at the cars submerged. So much flood, extreme flash flood. This is what I mean by flash flood. So the 3 sustainability principles: economic, social, and environment, what we call the triple bottom line. Not just look at the economic cost only, but you look at the social responsibility and the environmental responsibility. And then these are connected to the 5 principles of the 5 objectives of the integrated water resources planning: the water supply benefit, economic benefit, societal benefit, the implementation benefit, and the environmental benefit. So we had to keep all that in mind. So we started the plan development process, the plan methodology in 2016, development of the demand side options, the supply side options, and then we developed different portfolios. How do we meet all those demands? And they scored the portfolios, and finally make the plan and took public input throughout the plan process. The portfolios basically are basically theme groupings of options to meet the needs. So demand management as well as the water supply options. We have to do both the demand side as well as the supply side. And the process develops up to 5 theme portfolios. Up to 2 hybrids will be formed for high performing options. And then portfolio were scored and analyzed, process evaluation of trade-offs, like do we use this or that? How much of each one to use? Do we use 60% of this and 40% of that, or 50-50 or 30-70, all of that. And then all of that leads to then the plan recommendation. So initial portfolio theme was to minimize the cost, maximize water conservation and environmental stewardship, because Austin is very pro-environment. They are willing to pay a little bit extra to improve the environment, to improve the water quality. The public demands that. And so minimize the implementation challenges, maximize water supply and reliability and climate resiliency, and maximize local control. So all of that. So we took public input from Austin Water as well as the Water Forward Task Force. These are the citizen-based task force. And we were, of course, staff, we were advising them. We were the technical experts, but these were basically regular citizens who were appointed by the city council. So the analytical framework, basically, we knew how much water, what people use the water for. We had the river basin map. So precipitation, how many dry days, but so there's a lot of data modeling analysis. When there was a water supply model, water availability model called WAM, Colorado River Basin Water. We have the best hydrologist. We hired a consultant. He was just amazing to work with. He developed the water availability model for us, and then for the disaggregated demand model using the geospatial sector and end use. And then we were planning for the drought and period of record and worst drought. And after doing all that, then we put the climate change impact. We hired Catherine Hayhoe. She's a top climate scientist from Texas Tech University in Lubbock. She's an amazing communicator. She talks about climate change to a lot of people. And so she helped us to study what the effect of the climate change might be. And then all of that was analyzed using decision support and analysis. More indoor versus outdoors consumption, everything was broken down into really fine details. So let me not get into that little bitty details. So what we wanted to do was we wanted to plan not just for the historical drought, but we knew things would get more and more extreme events. And so we had to plan for drought worse than the recent drought. So the worst drought was in the 1950s, but we will say, oh, that's unusual. It's never going to happen. But we got the drought from the 2007 to 16, that eclipsed the 1950s drought much quickly. So lake inflows were in the worst, I already told you that. And then the 2.5 times lower than what they were in the worst of the 1950s. So we had to prepare for even worse than what happened in the 2007 to 2016 drought. So our modeling shows that droughts worse than this are possible. So we had to plan for that. So the way we did this was we had to look at a lot of data. Unfortunately, because the lakes were completed in 1940, so the data before the lakes, because the hydrology changed because of the lakes. So the data, the river flow data before 1940, we could not use that because the lakes have completely changed the hydrology of the basin. And so we only had about 77 years worth of record hydrology. But what we needed was 10,000 years of data to do this proper modeling. So we used the Monte Carlo method to simulate. So we did the extended period for record hydrology. So basically, what you will see in the next pictures is this is 4 panels. The first one shows from the actual record of 77 years of data. The second one shows this was adjusted for climate change. This is where Catherine Hayhoe's brilliant mind came in, and she did that. And then what we did was using the same data, we used the Markov chain Monte Carlo method to generate simulated 10,000 years of data, period of record hydrology. And then we adjusted that also for climate change. So you'll see 4 of these, 77 years, again, climate adjusted for 77 years, which 10,000 years of data and 10,000 years of climate change adjusted. So you'll see 4 panels, all right? So this is it. So in 2020, this is where we are. This is the actual data. In 2040, we're looking at, When there is red, that means you're trouble. We don't have enough water. Our biggest problem we saw was going to be drought. So we had to prepare for drought. These are the drought things. So this is, we're doing for 20 years, 50 years, and basically 100 years. We started the planning in 2015, so this goes up to 2150. So these are the analysis we did. So basically we have to be prepared for the needs during those red periods, what's going to happen in the future. Okay, that's right now, there are not that many. As we progress, go into the future, the climate change effect it's getting pronounced, and the population is higher, the demand is higher, and that's what happens. So this is what ABCD, these are the 4 panels we see here. So again, the key points about the estimated plan, and we're implementing an adaptive management approach. We look at things and how things are going, and we have to adapt, change things. Basically, decision points were present here, and there's uncertainty in the future, so it sort of diverges. But because of that, we have decision points in the midpoint. We have to make of course, every 5 years we're looking at that, and then on these midpoints we make some tweaks and changes. Options for moving forward: demand as well as supply, different options, many different alternative water sources, distribute, reuse, sewer mining, basically take wastewater straight from the sewer for the neighborhood and have a small treatment plant there, treat it, and then provide it for, let's say, for irrigation, for other toilet flushing and other usage. You can do a lot of things. And a lot of other direct potable reuse, indirect potable reuse, groundwater, desalination, all of these different options, and how we can improve conservation and how we can improve our supply options. Did all that. So with all that, we completed the work in September, and so I retired at the end of September. So this was the report that was submitted, and this was recommended by the Water Forward Task Force in their sort of the final meeting in October 9, not the final, they met after that too, but, and then the very next day, the Wastewater Commission, which is Citizen Appointment Commission, reviews everything that the Austin Water. 8 days later, surprise, surprise, what happened? We had a big flood. Here, our entire plan was really focused towards drought, because we knew drought was going to be the biggest bottleneck and handicap for us. So Mother Nature threw us a curveball, and we had a big flooding. Remember that little river I told you, Pyronellis River? There was a little trickle, you could jump across it, the water. This is that river. What happened was, it was as if a big atmospheric river or cloud, basically burst of cloud, came and parked itself over this river, Pyronellis River's watershed, and just rained there, just through basically what they call atmospheric river. It just, the water just dumped there. And that area had a lot of red clay, red silt, and all that red silt got washed into the lake, this humongous lake. Generally, in the past, whenever we have had a lot of rain and flood, that water used to get diluted by the rainwater coming from the other areas. But in this case, the rain was so localized, it just rained on that area. The other areas, we didn't get a lot of rain. So it just completely overwhelmed the lake. Look at this. It went to the large lake, went to Lake Austin, and then Lady Bird Lake. And this is Barton Creek, another creek, which is only like 20 miles away. This is about 20 miles west of here. The river came and dumped it on the lake upstream, and then the silt made it this far back. And here there was not much rain. And so this creek is very clear. You can see the contrast. There was so much silt, it completely overwhelmed our treatment plant. This is something we had not planned for. And this was of such magnitude. Whenever we used to have this silt load coming in, they used to last maybe a couple of hours, 4 hours at the max, and the plants could easily handle it. But this one lasted for 2 weeks. The plants really struggled to keep the turbidity low in the treated water, because turbidity is really critical. You have to have clean water, otherwise it doesn't meet the requirement. And finally, after, they started on October 18, right? Sorry, 16. And finally, on 22, after 6 days, the plant just couldn't manage the increased silt load. I remember, so basically 3 weeks after I retired. So the first time the city of Austin had to issue a city-wide boil water notice. There had never been like that. There was always, if we issued a boil water notice in more than 100, almost 110 years, it was for a local area. If suddenly there is an accident and a pipe breaks in a neighborhood, the pressure goes down, and so out of abundance of caution, when the pressure goes down, we fear there could be contamination. So we warn people immediately, saying, hey, please boil your water for 3 minutes before you drink it. But on this one, the entire city, the 10th largest city in the US, had to do that. This became international news. It was embarrassing for us. And then basically what that does is it reduces the confidence of the customers. They don't trust them, because when this happens, they say, well, maybe the water is not good. Even though we ultimately found, even though the turbidity was high, the water was perfectly safe. There was no bacteria, because we thought high turbidity would lead to high bacterial level and people get sick. But nobody got sick. Nothing happened. The water actually turned out to be, it actually met the standards, except for the turbidity. But out of abundance of caution, we have to issue the notice, because as soon as the turbidity goes above a certain standard, you have to issue a boil water notice. And so our biggest concern was for drought, but Mother Nature surprised us with a highly localized flood. So this is what happens. You prepare for something, and something totally unknown comes out of the left field. That's what happened here. So anyway, so now you've seen this slide before. So the 9th and 10th, and in between, in late October, just a few days after that, we had the big flood. And finally, in November 29, the city council adopted it. So this was our plan that was done. So it just goes to prove that, Texans love to think they are the biggest, they are the best, they are the brightest, they are the richest. But it just goes to show Texas is just like the rest of the USA, only more so, because we're all suffering from climate change. I know that's been the case all over the world, Europe and all the parts of America, even in India. I know there have been flood and fires and drought. This is the biggest crisis we're facing. Well, coronavirus is the crisis for immediate now, but in the long-term future, I think climate change is a big problem. So that concludes my presentation. I'm sorry I took a long time. As you know, I love to talk. So if you have any questions or comments, we can take the questions related to this presentation. But if you want to talk about something else, anything, you ask me. I'm all ears. Let me know what your preference is. Any questions or comments? You liked it, you hated it?
Rohan, are you there?
Yes, sir, I'm here.
So at least he's there, so that's good.
So I request everyone to ask questions if they have any related to the slides, or anything related to IITK, or anything, whatever they want.
Yeah, anything. About my career.
Raj, I think what I will do is I'll leave because I have something to do, and these guys will be happier talking to you directly than with my presence, because they will kind of feel why should I be here when they're talking to an alumnus. So I have the dual hat of being alumnus as well as faculty. So I'll leave and I'll catch up with you later.
Okay, so, thank you very much.
Thank you. I will leave meeting so that I'm not ending the meeting. I'm only leaving the meeting. So Rohan, you are in charge.
Okay, sir.
Okay, thank you very much, Sujit.
Okay, Raj, I will talk later then.
I will talk later. Okay, thank you. All right, any questions or comments? Fire away.
Hi, sir. Good evening, sir.
Yes, good evening.
Sir, so I would like to ask, how was your experience with SoCE at that time? What were the events that you organized and all? Something about SoCE you want to tell us?
Oh, SoCE. In those days, you know, we were clueless. We didn't get many speakers like this coming and talking to us. Those were few and far between the institute. And I remember a few lectures in L7, some alumni came and talked. But I don't recall any SoCE lecture like this. You know, they did some more, it was more of a social interaction organization. We would go see films. The main things I remember from SoCE was they would organize film showing, like a new movie would be released, and then the very first day, there would be a bus and we could get a ticket, and we would go to the town in Heer Palace or whatever the theater names were, and see a film and come back. And so that was, but the professor used to come on that too. Once in a while, I think some professors came and gave a talk, or just had an informal meeting, just about career advice and this and that, their experiences. But, you know, of course, we didn't have PowerPoint back then. We didn't have the web. So, I mean, you all are so much advanced and lucky. I mean, you have the whole world at your fingertips. You're much more knowledgeable. We didn't know what Google was. Well, Google didn't exist, right? So all of that. And so now I think things are so much different. That we can be connected from across the world, and you, all of you, are so much more aware of what's happening around you, and then even across the world, all over the world. I think that has been the remarkable change. And so in our case, when I look at it, I mean, we were clueless at your age. So you are very privileged compared to us in that sense. I mean, because of the COVID, I couldn't spend as much time as I wanted to. When I was a visiting professor, I spent most of my time here because of COVID. But whatever little contact I had there, the students are bright and very knowledgeable, and the future is bright for all of us, with you guiding us in the future.
Thanks a lot, sir.
There's a
Yes.
question. Meet Sayya,
Yeah.
would you like to unmute yourself and ask the
Yeah.
question?
Hi, sir. Good morning, sir.
Good morning.
Sir, I
Good
had a
evening for
question.
you.
Yeah, sir. Good evening, sir. Sir, I had a question regarding the forecast that you made, that the tech Austrian department made. You had about 77 years of data, and you are doing this project for 100 years. And the data that you did with, like the simulation that you did with Monte Carlo, was for about 10,000 years. So
10,000,
obviously
yeah.
there will be a lot of variability involved with the kind of predictions that you made, right? Because
Yeah.
from 77. So sir, what are the risks associated with that? Because we can see like a 100-year project like that would be a multi-billion-dollar project. So like, how did you, like, first of all, what are the risks involved? And second, what steps did you take to mitigate those risks? Like you
fact,
said, every 5 years you plan something. So how was that planned? How was that incorporated in the plan?
Yeah, no, in fact, the Markov chain Monte Carlo simulation was used to minimize that, because we felt that only 77 years of hydrological data is not enough. That doesn't give us enough confidence. But so we use the Monte Carlo method to simulate, to artificially create the 10,000 years of data. You know, that was the plan. That was to actually improve the reliability of the prediction.
But sir, like,
Let's
10,000 years of,
let's hope it pans out. Let's hope it pans out. Instead of just making a prediction using the 77 years of worth of data. See, that's the beauty of the Markov chain Monte Carlo method. Is of course it would be best if we had 10,000 years of data, but we don't have that, right? So this is the next best thing we could do. So this was done to minimize the uncertainty. I mean, basically by creating that data, and then you see what I'm doing, what I'm saying?
yes, sir. Sir, then also
because we didn't have enough data, so that was the reason for doing that. And then once we did that, then we put the climate change effect on top of that.
okay, sir. And sir, what did you do to build risk mitigation plans within the project? Because 100 years is a long period. Obviously, like you said, like technology will be changed, so there would be some plan for mitigation.
Yeah. Well, we basically looked at different alternatives, different sources for water, because right now in Austin, there's almost a taboo for talking about groundwater. They say, no. Using groundwater is not good. We don't want to use groundwater. We've been lucky so far, but we came pretty close to losing our river being completely dry in 2011. And so we have to think of the unthinkable, because pumping groundwater is a double-edged sword, which is good. And a lot of places we use groundwater. For example, in IIT Kanpur, it's all groundwater. But what happens is, when your withdrawal rate is higher than your recharge rate for groundwater, then the groundwater table starts going down. It's depleted, right? So what you're doing is essentially the water that has accumulated in the aquifer for millions of years, you're withdrawing it in just a few years, and that's happening all over the world. So it's leading to land subsidence, collapse, all sorts of problems, and that's just not sustainable. So what we can do is use groundwater only in case of emergency, and then when the next flood comes, replenish it. Put the take the water from the river, which there's a lot of water during the flood, and when the plants are not used, let's say during winter time, when the demand for water is less. Summertime there's more demand because people are using more water. They're irrigating their lawns and gardens and taking more showers than in the winter, and so the winter demand falls. So that's when what we could do is treat the water and then put the water into the groundwater level, so bring the groundwater level up, and so that you can use it during the next emergency. So basically try to smooth out the thing. I mean, the total amount of rainfall may not change, but there are a lot of big gaps, big drought period and the big flood period, and they're getting more extreme. So that, and a lot of the other things, options. So there are many options. So we have not basically said this is exactly what we'll do. Those can be decided later, but here are the options. We've laid it on the table. And so we are moving towards using more reclaimed water, turning the sewage into water. That has, of course, had been done. The first time it was done was in Windhoek, Namibia in 1968. It's still people are drinking that water and has had no public health problem. And in Texas, the first time they did that was here in Texas, in the U.S., in a place called Big Spring, and the city, Wichita Falls. So that was sort of unthinkable. People said, "Are you kidding? I will never drink, treated sewage." But when push comes to shove, when there's no water, and that water is good, we have the technology to make it really, really good. They're better than anything you can get from the river, and so
sure.
That's what. So we're planning for all that. So there are different options. So as the technology and the things change in the future, people have a choice of choosing whatever the different from the different portfolios. Those are the portfolios I was describing there a bit earlier.
Rahul ji, proceed with your question.
Sir, good evening. I'm Rahul, sir, and like you said about the flood times and the drought times, and I am quite fascinated by the presentation in which you have actually given up this IWRP, Integrated Water Resource Plan, for both the things at one place. But India is a country where we always face these kind of things like drought conditions in the western side of the country, and the flood situation almost every season towards the eastern side of the country. So, may I know, sir, my question is that once you mentioned about the principles of sustainability, like economic, social, environment, and you spoke about the five IWRP objectives related to the water supply, economic, societal, and and environmental benefits. So will, as per your experience of these 50 years, and since you have been an alumni of IIT Kanpur, so you must have seen and you must have correlated, you come up with a beautiful plan in Austin. Can we have these kind of same objectives for the IWRP in our country also? Or are they having some kind of variation if we relate to these 5 objectives and try to implement same kind of plan for our country?
You don't have to use exactly this. I mean, each you have to use whatever is appropriate, for the society, for the, there are a lot of, you have to look at the societal, meaning the cultural and a lot of other aspects. There are political aspects, technical, societal, environmental. So, and then there's the nature comes in, right? The hydrology and the temperature and whatnot. But I think the basic goal is, of course, the greater good for the people. I think that's ultimately what everybody wants. It is possible to do that. You really alluded to this thing about, Eastern India, there's a lot of flood, and Western India, there's always drought.
So why can't we have a bridge between those? I mean, the query is that
exactly,
why can't we have
exactly.
At one place something is deficient, at other place it is in excess. So why don't we have this kind of bridges, so that we can have the geographical location itself is providing us an opportunity to just solve both the problems, but still we are not able to do it since last 75 years of our independence.
No, because water issues are really local. It's water, is heavy, and so it's very difficult to transport water. So unless your energy cost is extremely low, then it's difficult to pump water or bringing water from a long distance, like through a canal and whatnot. You can do to a certain extent, but let's say even in Texas, I remember the very first in the 50s when the first the last drought of record, now the 2006 to 2006 to 18 drought was the worst drought, but before that it was the 1950s drought. What happened was Texas said, "Oh, we cannot survive with this drought, so we need to have a Texas water plant." So they built a whole Texas state water plant, and thankfully it has continued. But the first one, basically, they have this idea that, East Texas has a lot of water, a lot of rain, just like in India. Eastern India has a lot of rain, and West Texas is very dry. So we're going to build big canals and pipelines to connect all this, bring all the water from the east to the west. That never happened because it's too expensive, and also people are very possessive about water, the water rights. They don't like to give their water, so it's all local. So you have to have sort of a micro equilibrium. Every area you have to sort of live within your means. It's not. I'm not saying it's just totally impossible. I think for the greater good, I think you can convince people that it's in everybody's interest, because they don't need all that water. There is flooding them. So why not share that water? But the main thing is sort of transporting that water is a challenge. And if it can be done all by gravity, it's well and good. But if you have to pump, that's and then another thing I didn't even touch on this is maintenance part. All over the world, what we do is we think building new things, designing new stuff. There's a lot of glory and a lot of money in that. We love the engineers who design and build, and their names are there. If you go to a building, it's designed by this architect or built by this engineer or the contractor. Their names are there. There's a plaque name, and the Pradhan Mantriji will come and cut the ribbon, and everybody eats a samosa and chai, and drinks chai, and everybody's happy. They get their picture taken. But what is more important, I'm not knocking down the design, the engineering work, but what's even more important than that is the work done in maintaining that, operating and maintaining that building or dam or whatever structure you build, and keeping that running for a long time, for the full life. That is the more challenging thing, but there is no glory and no money in that. You will never find the names of those people. For example, at a treatment plant, you'll find the name of the engineer, but you will not see the name of the operators, who has a much more difficult job of running it 24 hours a day, 365 days a year for 50, 100 years. To me, that as a society, we have failed because we have not put the operation and maintenance, the operators, on the same level as the engineers. We need to glorify them. We need to make the maintenance and operation just as sexy as the design and the concept. So because the other job is much more difficult. We don't give money. And so what happens, things fall apart. You know, these large civil engineering projects, they have a long life, 50, 60, sometimes 100 years. But if you don't maintain it, they'll fall apart in just a few years. And that is just a waste. So our philosophy seems to be, you know, build, and then neglect and rebuild at greater cost. So what we need to do is, whatever we come up with, we better make sure we have the wherewithal, the funding, and the willpower. The main thing is the political will to make sure that we maintain it. You know, just building something is not going to solve the problem. You know, we can build a lot of things. I mean, it's just like, would you buy a bicycle and then never put any oil for lubrication, no grease there, nothing, no, don't put air in the tire, don't change the tire, then the bicycle will fall apart. Or the car or anything, it's the same thing. Even with the building has to be maintained. Even our clothes have to be maintained, right? They have to be washed. Even a person has to be maintained, and they have to take care of their health and whatnot. Just making babies is not enough. You have to nurture the babies and let them grow and take care of them. It's the same thing with material things we build as engineers. And that is, I think, one of the biggest failures, in my opinion, of us as a society all over the world. So we build things and then we don't pay attention to what's going to happen after that. Who is going to do that? So I would say build something, but if you cannot maintain it, why build it? Don't build it, because otherwise it's just a waste. But people feel good because it's a monument to themselves. They want to see their names there, and they can claim, we did this, we built this. It'll work for a few years, and after that, through absolute neglect, it just falls apart, and nobody's held accountable. And that is happening all over the world. Maybe more in some part of the world, but less in some others. But it's the same thing over here also. I mean, here, of course, they have more money, so they have more money to throw at it. But just throwing money won't do it. You really have to have the respect and the dignity for the workers. But every little work, no matter how trivial the work is, if somebody does a good work, doesn't matter how trivial, that person should be respected. There is a wonderful quote. Basically, it says, any society that thinks philosophy is exalted, is a profession because it's a higher level thinking, and plumbing is low level. It's not. It's really doomed for failure. Because they will say, but what we should do is a good plumber, an excellent plumber is better than a lousy philosopher. But what we think, philosopher is a professor, he thinks, he writes. So philosopher is always been in high category. But if he's a lousy philosopher, ignore them. If he's a good plumber, recognize them. Because otherwise, neither the philosophy nor the pipes will hold water. And I can send you the exact quote. Sorry.
Yes, sir, thank you.
Did I answer your question? But basically, yes, it is possible to use the similar kind of a thing. You may have to adopt them for different contexts, for the Indian context. We don't have to blindly copy the West, because things are different in different places.
Actually, sir, in the last 10 years, sir, there is a data, sir, like in the Rajasthan area, sir, for example, which is very near to Delhi, like Alwar location, the wells are drying up, so the groundwater is totally drying up, sir. And even the UP area also, sir, in last 10 years, I have seen, sir, a recent experience which I felt that 30 feet of water level has gone down, sir. So that means the water we are actually, what you have right now, in the presentation you have mentioned, that we are drawing more vis-a-vis conserving it, sir. So that means we are actually making our land dry, but we are not able to conserve it. So this is a great challenge. That's why I think Mission Jal Shakti has come up in India. But they are also working on it. But I find that that is only for the cleaning of these Yamuna and Ganga, but not in the conservation of the water and having the reservoirs, like you have mentioned Austin, Texas, which has happened, sir. So I was just maybe, sir, I may be pitching in some day, sir. So I'll be requesting your expert advice, sir. So please allow us and give some valuable advice so that seeing our geology.
That is an excellent point you made. This is what happens. I mean, really millions of years of that water, that was recharged there. We're using it in a few years, and then what happens next? You can't keep going further and further, deeper and deeper. And when you pump out too much groundwater, the ground will collapse. There will be a lot of ground subsidence. Even here in Texas, it's happening in the Houston, Galveston area. There's a whole Houston Galveston subsidence district, which is watching how much water you can pump. So we need to have some regulation. So we need to do some groundwater recharging, and then people are making this recharge. But even there, you have to be very careful the way you do it. If you're not careful, you will end up putting a lot of dirty pollutants, like somebody puts some motor oil or some other chemicals. If that seeps into the groundwater, then your groundwater is contaminated, and then you can't use it again. So you have to do it properly. A lot of these rainwater recharge people are building everywhere. So it has to be done properly, designed properly. So again, design is very important. I'm not knocking down the design, but again, what we do is we build a recharge facility, and then nobody maintains it. That's another problem. So somebody has to watch it, make sure none of the nasty pollutants go in, and that is the only way path forward. Otherwise, you really have to look at every drop of water and then plan for that. I mean, this is what Singapore has done. Singapore is a small city. They don't have a big watershed upstream. It's just a city state, right? And so right now they're importing water from Malaysia, and that contract expires in 2060. But now Singapore is preparing to 61, I think the contract expires. So they are afraid that Malaysia might say, oh, sorry, we can't give you any water. We need the water here because Malaysia is growing. So they are preparing for the eventuality. And so they want to be totally water sufficient. So they're using desalination, reclaimed water, all of the water, every drop of water, storm water, to make sure they are self-sufficient the year before that their contract with Malaysia expires. I think when this is, for them, it's an existential question. In the US, we use 3 to 5% of our treated wastewater. Israel uses, 70, 80%. Singapore uses about 35% now, I think, but they're trying to increase it. So when you are pushed against the wall, you have to do it, but we cannot put our head in the sand and say, this is the way it has always done, so we're going to keep pumping it out. And that has been a severe problem. And as you said, UP, Rajasthan, all over the world. I mean, I'm originally from Nepal, and I see the same problem in Nepal. They are just pumping groundwater indiscriminately. The government pumps, and the people pump, and those with the biggest pump win. And so somebody puts a deeper well, and so they put a big pump, and then the neighbor does the same thing. He says, I want to go even deeper than that. And there's no control. And so that, I think, is dangerous. So there needs to be some regulation. There also needs to be public education and understanding and a discussion, saying that we're all in this together. Our survival is together. We cannot, it's not just for the one with the biggest pump wins, but we're all in this together. So I think we need to forget our individual this thing and look at the greater good, the greater societal good. I think greed has taken over, and people say, well, why can't I have that? This is my right. Yeah, that maybe you're right, but that's also hurting a lot of other people. So these are some of the difficult things that we have to deal with. In fact, one of the things I really appreciate in the IIT Kanpur education was, back when I was here from 71 to 76, it was a 5-year undergraduate program. And every semester we had to take at least one class in humanities and social science. And to me, that was really fabulous. That has really benefited me because the technical solutions are easy. Generally, you can flip a switch. There are formulas there, the books, the design things. But it's the societal problems, the human relations problem, those are the difficult to do. And I think that's where we need humanities and social science. We need sociologists, we need anthropologists, we need cultural people, we need history, all of that. I think it is really, really critical. And that I find it is much more important. I mean, I spend a lot of time going to public meetings, discussing things with the people, the residents around the project site, or the citizens there, whoever is interested, want to come, welcome to come attend, answering their questions, making sure projects, we explain the projects to them in the language they can understand, and then get them to accept it. Because if they don't accept it, we're doing it for the public. If they don't accept it, if we don't have their support, then it can't go anywhere. So getting the public acceptance is important. Not just for the long term, not just in an irresponsible way, saying, yeah, I'll do this for you, so please support this project. But really in an unselfish, what's good for the society kind of way.
Okay, sir.
Yeah. And the problem with water is, I guess if we could solve the problem of energy, then we could move water from everywhere. We could desalinate all the water from the ocean and bring it everywhere, right? So even Rajasthan can be the desert can be all green. We'd be growing green mangoes grown in Rajasthan. But that still remains to be seen. Energy is still expensive, and moving water is difficult. So we really have to, water issues are local, and we shall see. These are difficult philosophical questions.
Okay, sir. Then Mudit, please ask your question.
Yeah, go ahead.
Good morning, sir. I'm Mudit,
Morning.
and I had this question which was, after doing your bachelor's, how did you decide that you wanted to pursue environmental health engineering? Like, I am in my second year and I'm studying geodesy, I'm studying air quality modeling, I'm studying sustainable development, and I'm not sure about it. So what would be your words for someone who wants to pursue research within the within the department?
Excellent questions. Of course, everybody is different, and my advice is really not worth that much, because you have to find your own path. But let me give you my experience. I was in civil, and my brother, who is 9 years older than me, he's an architect in Nepal. He's retired now. He was the third architect in Nepal. There were not many architects. There were a lot of engineers, but among the architects, he was the number 3 architect in Nepal. And so he came back with his architectural degree in 1970 when Nepal started working. And a year later, in 1971, I came to IIT Kanpur. So I thought, well, my brother is an architect. I'll study civil engineering. I'll specialize in structures. I'll take all my electives in structures, then we can work as a team. I'll do the structural design, you'll do the building design, and we'll make a great team. Brother and the Bhattarai brothers, right? So that was, I thought my career was decided. But after I came here, came to Kanpur, the whole world opened. Nepal was small. I was a little frog in a little well-cooked manduk. And Kanpur was that suddenly opened up the world. And we saw world-class professors, the library, the books, and the knowledge. I mean, the way we were taught, the atmosphere was totally different. And in our case, the first 3 years were core courses. You know, all the branches of engineering studied together. And in the 4th year, you know, we started civil engineering. We were into separate last 2 years where you went to individual departments. And the first semester I took classes in structural analysis and I did very well. I thought, this is good. I'm going to be good. And the second semester, took my first environmental engineering class. And I loved that. I liked it so much. I said, this is it. This is what I'm going to do. It took me less than 2 weeks. So I wrote to my brother saying, hey, brother, you know, I know we had said, you know, I'm going to be studying structural. I'm going to go to environmental. So after that, I took all my electives in environmental engineering. And I was just hooked. It was fascinating. I took classes in microbiology. I mean, I was very fortunate. The professors were great. And I spent all my spare time in the environmental engineering lab. And the passion was so much. And I did my project and the swimming pool had just opened that year. And so I did my senior project, the B.Tech project on the swimming pool water quality, you know, with 4 other friends. You know, I think 4 or 3, four of us, yeah. And it was a group project. And so then I decided to go for further studies, you know, came here. Again, I chose environmental engineering. That was decided pretty early on, just on the basis of just one course in environmental engineering. I was really fascinated. I liked chemistry. I mean, I like all science, but somehow chemistry, I have a sort of a intuitive feel or insight. I like it. I mean, when I was in high school and then even when I was doing intermediate in Nepal, I used to enjoy reading chemistry books. I mean, I used to read it lying in bed. I used to read it like a novel. So I liked chemistry, and so there's chemistry involved, but it's not just chemistry. You know, environmental engineering is a very multidisciplinary field, right? So you need everything. You need mechanical engineering, you need electrical engineering, you need hydraulics, you need hydrology, you need chemistry, microbiology, chemical engineering. So all of that thrown together. You know, we beg, borrow, and steal from everybody, and then we make things work. And Mother Nature is very forgiving. In spite of idiots like me, things work. Some of the plants I have designed still continue to work and surprises me, you know. And so it's the education that I got at IIT Kanpur was extremely helpful. I mean, after 5 years there, coming to the US, I thought it might be very difficult. It was relatively easy. I think it was the caliber of the students as well as the caliber of the professors there. So I had to work hard, but it was more of a cultural shock and getting used to the new system. But technically, I think we were prepared to take anybody in the world head to head. I mean, so that's IIT is a tremendous gratitude I have for that. But the government of India established IIT, and I'm not even Indian, you know. Well, my mother was born in Pondicherry of Nepali parents. So she was an Indian citizen until she married my father, and then so I have some Indian connection, even though so I consider myself a Nepali. But I never felt like a foreigner or outsider. Nobody treated me like, oh, you're a foreign student. Nothing. I mean, I was perfectly at home. Those were the best years of my lives. I mean, I still have very fond memories of Hall 3, Hall 1, all the lecture halls and the Western labs and the Western lab extension and all the labs and faculty building, meeting professors, doing things, running all over, you know, the library. So the campus is etched in my memory. So enjoy your time there, make friends, discuss things, study, but broaden your outlook. I think those are important things. And do whatever excites you. But again, just because I did something doesn't mean everybody has to do that. You have to find your own way, you know, what works for you. whatever makes you happy,
Yes.
whatever excites you. Because I think the world has opened up. I think even in India, the opportunities are tremendous now, back from back when we were there. For us back then, doing an internship was unheard of. I think you have opportunities for internship or doing some practical work, even either with professors or with somebody else, here and there.
Yes, like
That's
now.
much more common here in the US, but less so in India at that time. But in Nepal there was really nothing. In Nepal, we were in the backwaters. So we're in the dark ages. Sorry, go ahead. You had a question?
No, so like I was agreeing, like you nowadays, like intern is getting like more in the like everyone is now wanting for doing an intern before the placement so that they have an experience in the field of job.
Yes.
Yeah, I mean, you can explore. That is one thing that I think I admire about the US education system is here they're very flexible. Over back home, I think our sort of fate is decided pretty early on. By 7th, 8th grade, you know whether you're going to study biology and go to medicine, or you're going to study math and physics and go to engineering. Whereas here, people are very flexible. People do all sorts of things, like even for going to medicine. I have like my doctor, her undergraduate degree was in music. And then she she went to medical school. She's a fabulous doctor. She was at the top of her. I'm sorry? So that flexibility, it doesn't matter. I had some of my professors, like I had one professor here who was my friend. I mean, I saw a lot of films, so he was interested in films. He had a bachelor's degree in physics from Princeton, and a master's in philosophy, again from Princeton, and then PhD in Russian literature from Harvard. So he taught Russian literature here for about 30 years. And then he decided he wants to study this. What is this Russian literature? What am I going to do with this? This doesn't help anybody. So I want to go to medical school. And he went to medical school, became a doctor. So
Very interesting.
if I tried to do that back home, they would laugh at me. But here they don't. That's the flexibility.
Like they're only changing the like going from engineering to any other field. Like people will say, like, why you even did engineering when you don't want to do when you want to do an MBA or go for anything like that.
Yeah, exactly.
That's interesting.
Yeah, MBA is okay, but even MBA they think is a waste. But I have a lot of my friends who were fabulous engineers. I mean, they were brilliant students, but they didn't do a day of engineering. They just went into management, and they have been amazingly successful. One of them is Mr. Muktesh Pant, Mickey Pant. He just donated a huge sum of money to establish the School of Medical Research and Technology at IIT Kanpur. My classmate, he's a chemical engineer, but he didn't practice chemical engineering.
Sir, I have a question for you.
Yes, sir, go ahead.
So what is your take on the statement that there are less opportunities in the core civil engineering? Is it just a myth or a fact, according to you?
Well, I guess that depends on the local situation, where you are and where you're employed. I think that there is need for civil projects and civil construction, because India is growing and people are growing. They need houses, they need roads, they need water, they need airports. All of those things are needed. For all of that, you need geotechnical analysis, soil, foundation design, all of them. So every field is needed. What I am surprised. I think part of it is maybe because the economy is driving that. Right now, I think the IT has the glamour. People think, wow, there's a lot more money in IT. So everybody, no matter what their degree is, they just want to do nothing but IT. It's just like either everybody wants to go in management. And what I'm surprised by that is, let's say there are 1,000 students. Don't tell me all 1,000 students, they're only interested in IT. I think that's part of the societal pressure or the economic pressure. That's what is doing that. I'm sure there is somebody, because we can't just go, we need brighter minds to build better roads, better structures, better, and thinking and for all this planning and doing that. So not everybody needs to do IT is what I'm saying. There's a lot of room for every different field. As long as, so you can't just have all the top people I cannot believe that all the top people, they only think of IT. There's some top people need to go to doing civil engineering stuff too.
Yes, sir.
But I think maybe I'd have the luxury of being here, where I don't have to worry about putting food on the table. My salary, even though it's a government salary, that did not make me very wealthy. But I don't have to worry about that. But in Nepal or India, that's the reality. People have to go wherever there is more money, and so that, of course, I think depends on the local condition. That you have to decide for yourself. But what I'm saying is there is room for a lot of things.
Yes, sir.
Excellence in any field is good, in my opinion.
I think
whether it's plumbing or philosophy, as I said earlier, plumber or philosopher. A lousy IT person is not any better than a great plumber.
Yes, sir.
So I mean, I would rather be the best plumber than the worst philosopher.
Sir,
Yes,
I think
Ashish,
someone
you have
wants
a question?
to ask a question.
Yes, sir. Sir, I wanted to ask, what are the career choices or job profiles a civil engineering student has, especially just after his graduation? Because as far as our placements are concerned, the situation is very pathetic. Only a minuscule amount of companies come like Tata Projects, L&T, and they recruit only just for one position, which is management trainee.
Wow. So that's what you were hinting at earlier. Somebody was okay.
Yes, so that's why. And sir, also in internship, not a single company for a core civil engineering profile came. So that's why more and more people, almost everyone is going towards the IT and trying to get a job in that.
Yeah, I'm sorry to hear that. So who is doing the work then? How does the civil work gets done?
So is it that only masters and only after masters one can get in technical jobs in civil engineering, like in design, things like that? Just after B.Tech we can't get into these kind of roles. Is it like that?
Well, it's becoming more and more so even here. But although except here, even with bachelor's, people have done well. And I think that's probably a better idea to get an advanced degree in engineering. I think that sort of getting a specialty, I think that makes you more sellable. There is talk about here that they have a professional engineer designation. You have, after your bachelor's degree, if you have 4 years of work experience, you're certified, you take an exam, you become a PE, like professional engineer. Then you can basically put your seal and certify it for government project. So there is proposal that for being a professional engineer, you do need not just bachelor's, now advanced degree, and for all practicing engineers. That merits our attention, which I think is good. I think advanced degree is good for these professional positions, but not. I mean, it's a desirable condition, but not the absolute condition, in my opinion. People with perfectly, just bachelor's degrees have done amazing work. Of course, your master's degree, I think, makes you, better sellable in the market. But I find it very sad that is happening. And but, like I said, you can do anything, but like, yeah, but the IT people will take you, right? That is the sad thing. Yeah,
Yes, sir.
I didn't realize how bad things were, because I used to wonder why is everybody just going to, that is the reason. Okay, that explains it.
Yes, sir. Also, after B.Tech, what the profile that I know, and I think that only project manager is the post profile that we can get into after our B.Tech. I can't think of any other post or large post that we can get with the B.Tech degree in civil engineering domain.
Well, I mean, the thing is, even after my master's, I didn't become a project manager immediately here. I just worked as a regular engineer for a few years before I became a project manager.
Yes, sir. I mean this. I mean the senior degree, a senior post that we can get after working
Ultimately,
as a
you
job.
mean.
Yeah, ultimately,
I see.
starting from a B.Tech graduate, ultimately
I
we
see.
can reach project managers. I can see any other profile in civil engineering domain. Can you
Wow.
discuss?
That is a bit shocking. So that's what I mean by, I guess I didn't touch on that. Sorry, I had made a different presentation the other day. We really should have a way of recruiting, hiring, training, and promoting people, so there is a career path for everybody. Whether it's engineers, managers, operators, plumber, whoever. Everybody, nobody should be should have to stagnate in this one position. There should be opportunities for rising up the ladder. It's just that people think, oh yeah, I think that's terrible. We pigeonhole people. Oh, he's an engineer, he's not a manager, or he's not the manager type. I think you can learn managerial things. I mean, yeah, some people have natural affinity for some are good in that, but given the I find that sad or pathetic, like I think you said that's not good. So these are the realities you're facing. See, I didn't realize all the. I mean, I used to wonder why. What is this? Everybody's not all of those people are really interested. Don't tell me that one person is not interested in civil engineering or mechanical or whatever. So that's the reality. Is that same for other fields also? Let's say for chemical or material
In
science.
most of the field, that's the case.
Wow.
Except MNC, electrical, and CSE.
What is MNC?
Mathematics and computing.
Oh, mathematics and computing. So is India going to do nothing but IT? I mean, so who is going to design their buildings? Who is going to bring the power supply to them? Who is going to design the power lines and the dams and the generators?
In future, we would export human capital for software and all, and we would import people for doing those things.
Why not use homegrown talent? Because there are plenty of smart people there.
Yes, sir.
Do those things, because those are needed. They're just needed. Yes. I mean, you talk about you were building toilets, by the millions, billions, and all over India. All that waste has to be treated, right? Somebody has to design that.
Yes, sir.
So you can't just build a toilet and leave it there. Those have to be maintained, and then they have to be designed properly. Who did all that work? So, or you just go dig a hole and is that a toilet or no? I mean, you have to do it properly.
So there are organizations which make projects and all.
Instead of Swachh Bharat, you'll have a ganda pani, everywhere.
we still need water, at least that
Yeah,
treated
exactly.
water
We need
for the
the
toilets.
IIT, the computer will not give you water.
Yes.
Even the computer generates a lot of heat that has to be cooled. So you need water for that also. So somebody has to create the infrastructure, right? I'm really shocked by that. You know, it's just, I think it's very short-mindedness. So I think there should be a market. So what about consulting companies? Even they don't, or government jobs. I mean, the government needs engineers, no?
Yes, sir, there are government jobs, but they are very less in number as compared to the number of civil engineers we produce.
Wow. See, when I was growing up in Nepal, I mean, we had nothing but almost all the engineers I had heard of, all the elders, they were all civil engineers. That's all we had. And there'd be a few, one or two mechanical or electrical engineers, and that's it. Engineer to us meant civil engineering, but now, of course, in engineering, that's how it started. You know, it was engineering, then it got separated. The name itself, civil, implies that, and so there is a military engineering and civil engineering. Civil did basically everything. Civil was the big daddy of all engineering, and I have a hard time believing that we've been sidelined like that. I think that's real short-sightedness.
Does anyone have any other question? No, sir, there's no question. So, sir, I think now we should conclude the meeting.
Okay, sorry, I took a long time.
No, sir, that's fine. No issues.
I hope you have you got something out of it,
Yes,
and then maybe even had a few laughs. If not at my jokes, at me. So.
Sir, the slides were really insightful, and also your jokes were good.
Okay. Well, remember, Austin is #1 and #2.
Yes.
Okay.
I would like to thank you for taking time from your busy schedule to be our speaker.
Absolutely. Let me know if you want me to come back and give me a different talk about a different topic, or just have a bull session. I'll be happy to do that.
Okay. Yes,
it's
sir.
Good to know that SoCE is thriving, and you all are doing these wonderful things. It's been very gratifying to me. So again, so thank you very much, and please thank Professor Sudhir Mishra. I'll talk to him also.
Okay. Thank you.
Yeah. Thank you all very much.
Okay.
Okay.
I'm ending the meeting now.
Okay.